When you tap your phone to pay for a coffee, the interface makes it feel effortless. A quick chime, a checkmark, and you are done. But beneath that smooth glass screen is a violently complex, distributed labyrinth of servers, fiber optics, and cryptographic handshakes. It is tempting to think of a digital wallet as a standard data entry app. You deduct $5 from column A, you add $5 to column B, and you sync it all using basic web APIs. That logic works fine for a weekend prototype, but try running 1 million transactions a second on that architecture, and the system shatters. Network connections drop, servers crash mid-update, suddenly money disappears into thin air, or worse, it gets perfectly cloned. You end up with database deadlocks and catastrophic audit failures. This chart maps out the core dilemma for systems engineers. On the x-axis, we have consistency and security, guaranteeing that money is never created or destroyed by accident. On the y-axis, we have availability and scale. That naive data entry approach sits right here in the bottom left corner, failing at both. Enterprise architectures must escape that corner, but network realities force a split. You surge up the y-axis, prioritizing infinite availability, or push along the x-axis to lock down absolute consistency. Surviving at scale requires making 3 unyielding choices: how you secure the physical edge, how you structure the database ledger, and how you coordinate distributed servers. The first architectural battleground happens right in the user's hand, at the point of sale. This is a strict choice between hardware isolation and software emulation. Apple relies on an embedded secure element. In this model, cryptographic keys and tokenized card numbers are permanently locked inside a dedicated, tamper-resistant microchip on the device itself. Because the keys live directly on the chip itself, users can execute an unlimited number of offline transactions. But the wallet provider is entirely bound by OEM hardware agreements. If the device manufacturer denies you access to the secure element, your wallet cannot be deployed, strictly limiting your global reach. Google took the opposite path with host card emulation. Instead of negotiating for physical chip access, HCE uses the host operating system to route NFC communications directly to the wallet software. This diagram shows software routing provisioning. A cloud server sends a tokenized account number to the app, bypassing hardware restrictions. But because the OS is vulnerable, it relies on limited-use session keys. These expire, capping offline transactions until the user reconnects. At the mobile edge, you are trading the offline reliability and security of hardware for the global reach and software scalability of host card emulation. Once the transaction leaves the phone, it hits the back-end system of record, the database ledger tracking the financial balances. Early-stage startups usually reach for standard relational databases like Postgres. The initial setup is fast, and the developer experience is universally understood. Routing fees through a single account forces row-level locks on every update, bottlenecking streams to 15 transactions per second. High-volume platforms bypass this using domain-driven sharding. Splitting one account into 50 parallel nodes eliminates locks, scaling throughput to 1 million transactions per second. The cost of this performance is a rigid development environment. You have to adopt an append-only architecture, where standard database update or delete commands are strictly forbidden. If you make a mistake, you cannot erase it. You must issue complex reversing transactions to balance the books. Moving to a purpose-built ledger trades immediate developer convenience for a mathematical audit-safe guarantee that phantom money cannot infect your system. The final architectural hurdle is maintaining transaction atomicity across physically separated microservices. You have to deduct the payment, update the inventory, and trigger shipping, all without anything falling out of sync. The traditional solution is the two-phase commit protocol. A central coordinator forces all participating databases to lock their records and agree to commit or roll back their local changes at the exact same time. For modern cloud applications, this is a massive liability. If the central coordinator fails, or if a network spike delays consensus, those resources sit there holding their locks indefinitely. It destroys system availability. The modern alternative is the Saga Pattern. Rather than forcing one massive lock, Sagas break global transactions into independent local commits. Each service updates and releases its lock immediately. If a downstream step fails, the system fires compensating transactions backwards to undo earlier steps. To execute this reliably, engineers use the transactional outbox pattern. By tailing the database's write-ahead log with tools like Debezium, Services securely emit these Saga events directly from the log, guaranteeing no messages are dropped. Sagas abandon the safety blanket of immediate consistency. You accept a system that is only eventually consistent in exchange for massive scale and fault tolerance. These architectural choices map directly to specific business realities and scaling phases. Consider a global payment service provider handling thousands of concurrent transactions. At that volume, you have to ruthlessly optimize for throughput and availability. That enterprise stack requires abandoning two-phase commits and traditional SQL. You must invest heavily in the Saga Pattern, transactional outboxes, and strict double-entry ledgers to scale without locking. Now, contrast that with a product team launching a closed-loop transit app or a regional gift card wallet. For them, getting the app onto as many mobile devices as possible is paramount. That team should lean heavily into host card emulation. You bypass OEM hardware restrictions, accepting the operational burden of managing session key expiration and robust cloud tokenization. In distributed financial systems, absolute consistency and infinite availability are mutually exclusive. Pulling hard on one lever forces a sacrifice on the other. You cannot engineer away these trade-offs. You can only look at your architecture, look at your business model, and choose which compromises you are equipped to survive.